we're going to continue on with our differentiating, and our function is y equals x squared times the sine of x times the tangent of x. Here we have three functions, and we didn't see a product rule for three functions, but we can see what that would look like. If I had like UVW, and I'm taking its derivative, then I'm going to think of this as the product of u and v times w. And by doing that, I can apply the product rule. So I would have uv, that whole thing prime, times w, plus uv times w prime, right? That's the product rule. First thing prime times the second function plus the first function times the derivative of the second function. And then I apply the product rule as needed, right? So here, uv, that product prime, is going to be u prime v plus uv prime, all that's times w, plus uv times w prime. What we'll see is we have u prime vw plus uv prime w plus uvw prime. And this is kind of like an expanded version of a product rule. And what you can see is you have u, v, and w in all three terms. And in the first term, u is prime. In the second term, v is prime. In the third term, w is prime. So that's how the product rule is going to apply here. Let's say in this case, u is equal to x squared, v is equal to the sine of x, and w is equal to the tangent of x. I'd like for you to go ahead and find and simplify the derivative. Somewhere along the line here, you probably had to make a decision about where to simplify and what to simplify. What I have is that y prime is equal to 2x times the sine of x times the tangent of x plus x squared times the cosine of x times the tangent of x plus x squared times the sine of x times the secant squared of x. The cosine divides out into the tangent, leaving me with the sine function, and that's as much as I did. In a previous example, we turned the sine of x times the secant squared of x into the tangent of x times the secant of x, and if you did that here, that's fine. But suppose we wanted to divide out, or factor out, I should say, any common factors. This way I can see that I have x as a factor that's common to all the terms, and the sine of x is a factor that's common to all the terms. And that might be something I'm interested in. It really depends on what I'm going to do with this. But here I'm just going to put a box around it and we're done. Next, we're going to find the equation of the tangent line to the curve. Y equals x plus the tangent of x at the point pi pi. Remember, the equation of a tangent line is going to be in the form y equals mx plus b. And we have that m is going to be f prime, or I should say y. It's going to be y prime evaluated at x equals pi. That's the first pi, by the way, because it's the derivative evaluated at the x value of the point under consideration. All right, we need a derivative. Y prime is equal to 1 plus the secant squared of x. Y prime evaluated at x equals pi is going to be 1 plus -1 the quantity squared, because the cosine of pi is -1, so the secant of pi is -1. The slope is equal to 2. Therefore, if we use y equals mx plus b with m equals 2 and the point pi pi, we've got that pi is equal to 2 pi plus b, which implies that b is equal to -pi. So the equation of the tangent line is y equals 2x minus pi. The point here, I guess I'm reinforcing how to find the equation of a tangent line, and that the introduction of trigonometric functions doesn't change that process at all. Now we're going to get into interpreting a derivative just a little bit. Find points on the curve y equals the cosine of x over 2 plus the sine of x, where the tangent line is horizontal. As you may recall, a horizontal tangent line means that y prime is equal to 0. This starts with, guess what? Find a derivative. I wrote y prime equals, but I'm not ready for that at all. Here we have a quotient, cosine of x over 2 plus sine of x. And what I'd like for you to do is use the quotient rule and find this derivative. After applying the quotient rule, I ended up with y prime is equal to negative 2 times the sine of x minus 1 over the quantity of 2 plus the sine of x squared. Now, of course, we're not done. That was just the derivative. We want to find where the derivative is equal to 0. Thankfully, the only thing that can make a fraction equal to 0 is its numerator. Therefore, in order to find out where y prime is equal to 0, we just need to know where negative 2 times the sine of x minus 1 is equal to 0. Or in other words, where the sine of x is equal to negative 1/2. Let's choose to go on the interval from 0 to 2 pi and not all possible solutions. X is then going to equal 7 pi over 6 or 11 pi over 6. Those are the x coordinates associated with this curve for which the tangent line is horizontal. Now, we weren't asked for the x coordinates, we were asked for the points on the curve. So now we have to use the fact that y is equal to the cosine of x over 2 plus the sine of x. So, 7 pi over 6, 11 pi over 6 for our x values. And when x is 7 pi over 6, the cosine of x is negative square root of 3 over 2. And that's going to be over 2 minus 1/2. That'll simplify to negative square root of 3 over 3. For 11 pi over 6, we have positive square root of 3 over 2 over 2 minus 1/2. And I can see that that's going to turn out to be the square root of 3 over 3. So we can say the tangent line is horizontal at 7 pi over 6, comma, negative square root of 3 over 3, and 11 pi over 6, comma, square root of 3 over 3.